So we've been talking about equilibria. When an ionic compound dissolves in water, that is also an equilibrium process, because as ions dissolve, ions also recrystallize into the solid. And so we have a term called the solubility-product constant, and its symbol is KSP. And this is essentially the equilibrium expression for the chemical reaction describing the dissolution of an ionic compound. So instead of calling it KEQ for equilibrium constant, we call it KSP, SP for solubility product. Just to remind you, solids are omitted from equilibrium expressions. If we have a very large KSP, that means that the concentrations of the ions are high and the compound is very soluble. If the KSP is very small, it means that very little of that dissolves, and so we say the compound is not very soluble. So in this example, we have barium sulfate dissolving in water. So you put barium sulfate in a beaker and you add some water, and then the forward reaction begins to proceed, and you get some barium ions and some sulfate ions. But you also have the reverse reaction occurring where barium and sulfate will get together and redeposit or recrystallize onto the solid. And so KSP, we write that the same way that we write equilibrium expressions. You take the concentrations of the products and you divide by the concentration of the reactant. But here the reactant is a solid, and solids don't change concentrations, and so we leave them out of the expression. So it's just the concentrations of those two ions times each other. Let's think about what's going on here. When one barium sulfate formula unit dissolves, we get one barium ion and one sulfate ion. So what can we know about the relationship between barium and sulfate concentrations? Could they be different? How could they be different? Okay, so let's think you have a group of married people. So husband and wife, husband and wife, husband and wife. They all come to this party, and some of them are going to, go over there to the men's room, and some go to the women's room. Could you have an unequal number of men and women in that room? No, because they came paired up. And here, with the barium sulfate, there's one barium for every sulfate, and so when it dissolves, we get the same number of barium ions and sulfate ions. And so we can say that the barium ion concentration equals the sulfate ion concentration because of where they came from. Now this is taking a solid and dissolving it. Now if you threw some sulfate ion in there, yeah, you could have it messed up. But if you start with the pure solid and you're just dissolving it, for every barium ion you get a sulfate ion, and so their concentrations have to be equal. So KSP values can be found in lots of different places. This is a table from your book, and you'll probably need to refer to this to do some of your homework problems. KSP is a measure of the solubility of a compound. If we look at this one, copper sulfide, we see that its solubility-product constant is 1.27 times 10 to the minus 36. That is an extremely small number. Mind-bogglingly small number. And what that tells us is when you put copper sulfide in water, there are very few ions that form. Almost none. If we compare that to the one right above it, calcium sulfate, that has a solubility-product constant of 7.1 times 10 to the minus 5. Still a very small number, but considerably larger. If you have a solubility-product constant that is, say, 5 times 10 to the plus 5, then you know that it's very soluble. So all of the compounds in this table have small solubility-product constants, and so we say that they're not very soluble. But any ionic compound is going to dissolve a little tiny bit. So when we talked about things that were soluble and insoluble, and we had those rules, do you remember the rules for solubilities? Those were generalizations. All of these guys would be clumped into the category of not soluble. When they're not completely insoluble, when you put them in water, a few ions will come off, but not very many. But in some situations, it can be significant. So we need to know how to write expressions for KSP. So let's do silver iodide. To write the KSP expression, we need to know what the chemical equation is. So this will be in equilibrium as well. Let's back up a little bit. This is a solid. All of these, we're taking the solid ionic compound and dissolving it in water. So the reactant is a solid, and that's going to be in equilibrium with its ions. Okay, and so this is pulling from things we learned earlier. Silver and iodide, well, it's an ionic compound, and this is going to make an ion, which will be aqueous, and the I is going to be an ion that'll be aqueous, and they're going to have charges. What charge does the iodide ion have? -1, because of its position in the periodic table. And what about the silver ion? It's going to be +1. There's two ways you could know that. You could look at the formula and see, oh, there's one silver and one iodine. If the iodine's -1, the silver must be +1. Or you could look at the periodic table and remember that aluminum was +3 and we went down the stairs. Aluminum, zinc, silver. Zinc is +2, silver's +1. So here's our equation for dissolving silver iodide. Then we write the equilibrium expression. So the iPad and I are just not getting along very well these days. Maybe we need a vacation from each other or something, I don't know. He wants to go play games with Andrew. It'll be the concentration of the products raised to a power that's equal to their coefficients. Do they have any coefficients? No. The coefficients would be 1, and so the power would be 1, and so we can leave those off. We do not divide by the concentration of the reactant because it's a solid. And you can't really talk about the concentration of a solid, and it's not going to change, and so we leave those out. So there's the expression for KSP for AgI. Let's do calcium hydroxide. Again, we're starting with a solid. Now, the question is asking you for the KSP expression. Could you do this without writing out the equation? You could. If you wrote the equation out, do you have to include the state symbols? No, you wouldn't absolutely have to. I'm just putting them in there so that we can see clearly why we're leaving out the reactant. It's because it's a solid. So calcium hydroxide, we're going to get calcium ion and hydroxide ion. And calcium, we know from the periodic table, is in group 2. It's got a 2+ charge. And hydroxide ion, we know from memorizing, has a minus charge, -1. Or you could figure it out by looking at the formula. Here I'm leaving out the AQ state symbols because do we actually absolutely need those? No, we don't. The equation, though, has to be balanced. Is this balanced? No. Because over here in the calcium hydroxide, there's 2 hydroxide ions. So when this dissolves, we're going to get 1 calcium ion, and we're going to get 2 hydroxide ions. So we need a 2 here. So now we have our chemical equation. We can write the expression for KSP. It will equal the concentration of each product. Calcium has a coefficient of 1, and so its exponent is 1. Hydroxide ion has a coefficient of 2, and so it's going to be squared. And that's the expression. Any questions? what do we know about the concentration of silver ion relative to the concentration of iodide? Are they the same or different? We talked about this one with the barium sulfate. They're the same, thank you. Because we have one of each, one silver and one iodide. And when this dissolves, they come apart and we get one of each. They're all coming from the solid, so they have to be equal in concentration. What about with the calcium hydroxide? The calcium and the hydroxide ion, are those going to be the same? No, because for every one calcium ion, you get 2 hydroxide ions. So the hydroxide ion concentration is going to be twice as big as the calcium ion concentration. Okay? And there are some homework problems that are going to ask you things like that. And so you just have to kind of step back and think about it. So we can use KSP to determine molar solubility. In general, the solubility of a compound is the amount of that compound that will dissolve in a certain amount of liquid. And that can have different units. It could be, grams of sodium chloride in grams of water, or in gallons of water, or liters of water. But it's how much of that solid will dissolve in a certain amount of liquid. The molar solubility is relating to moles. So molar solubility. So it's the number of moles of the compound that will dissolve in 1 liter. So we can use KSP to figure that out. How could we determine the molar solubility of silver chloride from its KSP? And we'll use S to stand in for molar solubility, so we don't have to write that out all the time. Well, here we're already given the balanced chemical equation. So there we've got the equation. One silver chloride formula unit will come apart into 1 silver ion and 1 chloride ion. And we're given the KSP, so we don't have to go look it up in the table. It's 1.77 times 10 to the minus 10. Is silver chloride insoluble or soluble? Is a lot of it going to dissolve? No. We would consider it to be insoluble if we had to choose between soluble and insoluble, because the KSP is very small. Let's write the equilibrium, or the expression for KSP. We already have the chemical reaction. So KSP equals, it's the concentrations of the products, Ag plus and Cl minus. There's no coefficients, and so we have no exponents. I was trying to get a smudge off and a drawing on it. The kids play games on this all the time. And what do we know about the relationship between silver and chloride ion? Their concentrations. They're equal, right? So the solubility, so S equals, let's see how to write this out. S equals the moles of silver chloride that dissolve per liter of solution. The concentrations of these ions are in moles per liter. For every mole of silver chloride that dissolves, we get 1 mole of chloride ion and 1 mole of silver ion. So each of those equals S. So that's going to equal the concentration of the silver ion, which is going to equal the concentration of the chloride ion. Does that make any sense? Yes, thank you. Because I wasn't seeing any no's or yeses. I'm like, well, okay. So we can say that KSP equals S times S, or S squared. If I dissolve 1 mole of silver chloride, I get 1 mole of silver, and I get 1 mole of chloride, right? The solubility is how many moles per liter will dissolve. The concentrations are given in moles per liter when we calculate.
Is that number on the KSP,
Mhm.
would that have been on the chart?
Yes, that is on the chart. So it will, you don't memorize those because there's a zillion of them. They'll either be given to you in the problem like this one is, or you will have a chart available. Homework, you've got Google, right? But you've also have your book. On an exam, a KSP will either be given in the problem or a table of KSPs will be given. Good question. So for every silver chloride that dissolves, we get one chloride and one silver, so their concentrations are equal. The concentration is expressed in moles per liter. If we dissolve 1 mole of silver chloride, we get 1 mole of silver ion. So if we can figure out what the concentration of the silver ion is, that is the same as the molar solubility. You follow that? I got some people are like, yeah, go on. And other people are like, I don't know about this. I'd like you to understand what's going on. By the way, what we're talking about right now, this is not a big deal, okay? We've talked about other things that were big deals. This isn't a big deal. But what we come down to for this expression is that KSP equals the molar solubility squared. Can we solve for S? Sure we can. Question?
Why is the S squared?
Why is the S squared? That's a good question. Hopefully I can answer that. S is the moles of silver chloride that dissolve in a liter. That's called the molar solubility. For every mole of silver chloride that dissolves, we get 1 mole of silver ion. So the moles of silver chloride per liter that dissolve will equal the moles of silver per liter. The moles of silver per liter is equal to the moles of chloride per liter. KSP equals those two concentrations multiplied by each other. So what I'm trying to show you here is that the molar solubility is equal to the concentration of this, which is equal to the concentration of that. So instead of writing the concentration of silver, I can write S. So this is S, and here is chloride. Chloride is also equal to S. So KSP equals S squared. And things can get really gnarly when you have things that break up into more ions than 2. We're only going to do a calculation like this when you have a 1-to-1 ratio of ions. So it'll always end up being KSP equals S squared in this class. If you go on and take Chem 1B, completely different. But KSP equals S squared. So to find the solubility, we just need to take the square root of KSP. So S equals the square root of KSP. So you need to be careful on your calculator. This is where if you still have not mastered using your EE button, you're going to have trouble. So 1.77 EE minus 10. Take the square root of that. We had 3 significant figures. We'll just stay with 3 significant figures. 1.33 times 10 to the minus 5. And the concentration of that is the capital M, which I understand that we haven't talked about much yet, but just go with that. So if your calculator is not giving you that answer, I need to speak to your calculator for you. Some calculators, you need to press the square root button first and then type the number in. Others, you do the number first and then push the square root button. But if you use times 10 and then EE, or the little caret thing, or any of those other ways, you're most likely going to come up with the wrong answer, because when you use the EE button, your calculator treats it as a single number. You want to be clear to your calculator, this is a single number, I want the square root of the whole thing, not just part of it.
And then we label it with an M.
You label it with an M. Which, on the homework, it puts that in there for you. So we will be talking about a lot more about what the M means, but it's moles per liter. The solubility is moles that will dissolve in a liter of solution. And all those concentrations in all of these expressions are moles per liter. Any questions? Okay, we're going to do another example. Calculate the molar solubility of calcium sulfate. So a lot less information is given here. No equation, no KSP, nothing. Okay, to do the molar solubility, we need to know what the KSP is for calcium sulfate. So let's go back to the table and look it up. Calcium sulfate, let's get a color that we can see. There's calcium sulfate. 7.10 times 10 to the minus 5. That, we're going to need that. 7.10 times 10 to the minus 5. 7.10 times 10 to the minus 5. 7.10 times 10 to the minus 5. Okay, that's KSP for that compound. We went and looked that up. We need to have the expression for KSP so that we can find out what the concentration is. So the calcium sulfate, and we did barium, actually I think we maybe did calcium sulfate too, I don't remember. It was so long ago, like 10 minutes ago. So calcium sulfate will come apart into calcium ions and sulfate ions. It's awesome if you can put the charges on there. Okay, if you can't put the charges on there, you can still do this. What you need to know is when we're looking at this formula, there's one of these and there's one of the other. There's two ions, there's one of each. That's the critical thing. So then KSP equals the concentration of those two products, the calcium ion and the sulfate ion. Now in the homework, it will ask you to do the expression for things that are a little more complicated, but it won't ask you to calculate molar solubility except for things that are one-to-one. And so then we say, well, the concentration of calcium is equal to the moles per liter of calcium sulfate that dissolve. That's the molar solubility. So that was S. And the concentration of the sulfate ion is equal to the concentration of the calcium ion, which is equal to the molar solubility. So KSP equals the molar solubility squared. I think it's best if you understand how this works, but you could also get by with remembering that KSP, or actually even, if you're just going to memorize something, memorize it simple. The solubility is the square root of KSP. Because KSP equals the solubility times the solubility squared. To solve for S, we take the square root of both sides. So if you're just really not clear on where all this is coming from, if you memorize that successfully, you'll be good. So to find the solubility, we need the KSP, and we say the KSP is the square root of 7.10 times 10 to the minus 5. 7.10 EE minus 5 square root. We're going to keep the same number of significant figures, 8.43 times 10 to the minus third. And we'll just slap an M on that. Units get a little weird with solubility expressions. Any questions? No? Okay.